Hello and welcome. We are Team Coordinator, and I'll be presenting about our research Internode Latency Aware Cloud Streaming Scheduling Strategy. Our team professor is Professor Bernberg Stoller. Our teaching assistant is Dr. Shin Hyung Yang. Our team members are Zhu Junhao, Lin Yihan, Zhang Xiaoshu, and myself, Kishan Ravi. This is our table of contents. We have introduction, novelty, methodology, and finally results. The primary research focus for our research is assuming multiple tasks require execution on several servers, we want to select an appropriate method for scheduling these tasks. Our research is important as the default scheduler for Storm relies on minimal information, and it typically employs a round-robin approach. However, many parameters such as CPU, network usage, memory, and traffic are already readily accessible. Therefore, we propose to utilize the network and traffic data due to their ease of acquisition and the compatibility with other schedulers. It is quite intuitive to think about using the network condition and traffic. Given the following latency and traffic graphs, which do you think is a better scheduler? It is a no-brainer to see that the first one would be a better scheduling, as there is larger traffic on the lowest latency path. Therefore, more data can be sent in a shorter amount of time. Right now, there is a research called RStorm, or Resource Aware Storm. It is a standalone scheduler that makes use of the previously mentioned additional parameters. Our research would differ from this by existing as an extension that is capable and available to other schedulers. We will make use of the traffic data and also the latency to further improve their scheduling. We also introduce different algorithms in order to make use of the traffic data and latency for better scheduling. Our first version is a naive and global optimal algorithm, which serves as a subroutine for other versions coming up. In this version, we match the traffic data with the latency by using a ratio of both. The traffic is an abstraction for the task, while the latency is an abstraction for the network resource. Here, a lower latency means a better network resource, and hence, before we normalize the latency, we first take its inverse. Therefore, a low latency would have a higher sum. Next is our methodology. We first start the nodes. We then measure the min round-trip time. Here, we query both the NTP protocols and the TSC registers. Next, we run Apache Storm to get the scheduling. We then run the streaming benchmark, where we load actors and start the data generator. After that, we stop and write the logs. We then measure the minimum round-trip time again. We then collect the logs to Nimbus, and finally we download the logs, clean up, and stop everything. It is important to note that the latency graph and the traffic graph are both homomorphic, i.e. they are the same. We will be using this point to our advantage when calculating all the possible schedulings. We define a method to quantify how fitting a scheduling result is. Here, the lower the better. It is important to note that we always score the scheduler by how much traffic overweighs latency and not vice versa. Why? Consider the following two cases. In case 1, the first edge has negative 60 score, while all other edges have a maximum of 20% score. In this second case, we have the first edge having a negative 60% score, while the second edge has a 60% score. If we were to score how well a scheduler is by the latency overweighing the traffic, we would have both cases scoring a 60% score, which is unfair as we can clearly see that the first case would heavily outperform the second case. And therefore, in the case where traffic is very little compared to latency, we would automatically set it to 0. For our scoring results, we would consider all possible orchestration, score them based on the scoring that we've just mentioned, and we select the one with the least value. The good thing about this algorithm version is that it always yields a global best fit result. However, we call it naive because the ratio of traffic is not deterministic. Take, for instance, the following graph. If 10% of the time the traffic from A to C is heavier than the traffic from A to B, based on this algorithm, we would set the lower latency edge on A to B. However, this causes 10% of our scheduling to perform worse. And the second con is that though it's very unlikely, a topology with 1 million machines or nodes will make the start time long, as we consider all possible orchestrations and score them individually. However, scheduling takes place ahead of time, and this does not affect the runtime performance. But anyways, slow startup is still not desirable. Therefore, we came up with the second version of the algorithm called the cascading score. Usually, a scheduler should not be intrusive, i.e., it should work on its own. However, in this version of the algorithm, we need to mark the point of non-deterministic traffic. Once we have that marked, it partitions the topology into two groups as shown below, and it applies the first algorithm to each group individually. However, this still cannot fully resolve the propagated non-determinism at group B. Instead, we have successfully isolated group A itself to be fully deterministic. Once the partitioning is done, we then decide which servers go to which group. We start by normalizing the traffic and inversely normalizing the latency within each group, and we try all possible partitions of the servers and matching them with the group sum. Once we have decided the server partition, we then finish by performing the first algorithm within each group. Based on this second version of the algorithm, we decided to make a small minor adjustment and aim for performance. It is a simple variation from version 2a, but we do not perform group granularity matching. Instead, we set a threshold such that if there are more servers, an active partition is triggered without the need of a marking. The pros for this is that for n servers, partition n servers will result in groups of n and n minus n. And this is a great improvement compared to the first version of the algorithm. However, the con is that multiple local optimal results are not as good as global optimal results. Finally, we reach our results. For our cloud setup, as our experiments will be run on Google Cloud, we have the following nodes. TC001 and TC002 are the Zookeeper nodes. TC004 are the Redis nodes. TC010 are the Nimbus nodes for Apache Storm. TC011 and 012 and 020 are worker nodes for Apache Storm. And TC21 and 22 are Cloud Profiler data generators that serve as the source of all traffic. This is the example of a traffic log from one of the actors, and the visualization will be provided in the next slide. From the following graph, we can see that the x-axis is time in 10 millisecond intervals, and the y-axis is the number of events or tuples recorded in this actor. From this, we can calculate the total traffic data for this specific actor. This is the log file that is used to calculate the minimum round trip time. And here is the log that shows how we calculate the one-way latency. In the first column, we have the tuple index, a unique number for each logged tuple. In the second and third column, we have the logged time. The fourth column, we have a timestamp counter, and the fifth column, we have the CPU core number. Using this information, we can see the outgoing time of the tuple, the incoming time of the tuple, and using those informations, we can calculate the one-way latency information. As of now, our implementation for our scheduler is still under progress. However, from the results, we can see that we have obtained all the necessary information to be used in our algorithms. And therefore, our final results will be included in the final report. Thank you so much for listening.